Good morning, good afternoon, good evening, class. My name is Mr. Arosena, and today we'll be talking about continuity. So this is a continuation of the calculus that we've been studying in class last couple of days. I decided to skip the 2.4 section because it's a little theoretical and honestly not that important in the grand scheme of things. Right, today we'll talk about continuity. So continuity is we're probably very familiar with what continuity is. We just never actually described it. Okay, so for example, if I have a function, draw a line. If I have a function like this is a continuous function. Continuous functions are also like straight lines, like that. Those are all continuous functions. The continuity is just basically, is it a smooth flowing line of some sort? Right. That's what continuous is. And we've discussed lots of continuous functions before, like, again, straight lines, trig functions, polynomial functions, and so on. Now in calculus, we have a specific definition for continuity. Okay, and I guess in math in general, we have a specific definition for continuity. So in calculus, a function is continuous at a if the following condition is true. And remember, a is just a point on the x-axis. Okay? So the following condition must be true for a function to be continuous. The limit as x goes to a of f of x is equal to f at a. Okay, this seems kind of strange because I remember in one of my previous lessons we talked about the helpful hints for calculating limits, and one of the hints I had was effectively just calculate f at a. Okay. If it gives you a number, then the function, that's the limit of the function. Okay? You can use that check also to see if a function is continuous. So if a function is continuous at a if f of a is equivalent to the limit as x goes to a of the same function. Okay? If f of x does not meet this condition at a, then we call it discontinuous at a. And there's several different types of discontinuities. Okay, continuous functions are easy. Discontinuous functions are a lot more interesting. Right. So, as I said, there are three types of discontinuity. The first type is what we call an infinite discontinuity. Okay, and this is similar, well, it's similar to like asymptotes and things like that. Okay, I'll give you an example. Here's a function that shows an infinite discontinuity. And we call it infinite discontinuity because the function goes towards infinity. And it never actually jumps from across this asymptotic line, this asymptote. Okay, so this is an infinite discontinuity at x equals 0. So at x equals 0, you have an infinite discontinuity because the function is undefined at x equals 0, and the limit ends up going towards infinity. It goes towards infinity, never crosses that asymptote. This is an infinite discontinuity. And you can have infinite discontinuities going in opposite directions as well. So for example, like this. Here's an infinite discontinuity where it goes one side goes towards negative infinity, one side goes towards positive infinity. All right. Still considered an infinite discontinuity at x equals 0. Okay. If the asymptotes move, like for example, this is x minus 1, then the discontinuity moves with it. So the asymptote here is at x equals 1, so at x equals 1, this function exhibits an infinite discontinuity. And it doesn't really matter whether the function goes towards positive or negative infinity. What's important as far as continuity is concerned is that it just is discontinuous. It goes towards infinity at some point. Right. The second type of discontinuity is called a jump discontinuity. Okay. And as the name suggests, this literally means that at the discontinuity, the function is going to jump. So here's an example of it. Okay. This is plotting the least common multiple between x and x divided by 2 and then subtracting it by 0.5. Regardless, it illustrates my point very well with a jump discontinuity because here, here your function, use my mouse, your function is nice and fine here, and all of a sudden it just jumps at x equals 1 and at x equals 2. It just jumps and jumps and jumps and jumps and jumps. And that's really all a jump discontinuity is. It's just the function is really discontinuous, and it just jumps all over the place. Okay. So this function obviously discontinuous at several points. Right. And because it just jumps all over the place like that, we call those points jump discontinuities. So like for example here, at x equals 1, we have a jump discontinuity. At x equals 1.5, we have another jump discontinuity, and so on. Okay. The last type of discontinuity is what's called a removable discontinuity. A removable discontinuity looks like this. Okay. Now, this function is discontinuous at x equals 2. The graphing program doesn't show it very well, so I've shown it here explicitly. But if I don't show it, you kind of have to mouse over it. There we go. X equals 2 is undefined. There it is, undefined. Reason for that is because if I look at my function at x equals 2, well, then I get a division by 0. Okay? But we call this a removable discontinuity because we can plot a function very similar to this original function that will make it continuous everywhere. Okay? And that will be kind of my first example. Right. Whoops. Not quite. Okay. Let's go over this. Why is that called a removable discontinuity? Well, the function is x squared minus x minus 2 divided by x minus 2. Okay. Well, this is just a quadratic, and we can factor this. So the top can be factored as x plus 1, x minus 2. The bottom remains x minus 2, and we can cancel out the x minus 2 and x minus 2, so we get an equivalent function x plus 1. Okay. So this is what the function simplifies to. Now this simplified function has no discontinuous points. Okay. However, the original function, I'll highlight that here, the original function still has a discontinuous point. Right? The original function cannot be 2. Okay. Even though it simplifies to this, even though it simplifies to just x plus 1, the original function still cannot be x equals 2. So we can remove that discontinuity by simply plotting this one. So instead of using this function, x squared minus x minus 2 all divided by x minus 2, if I want to make it fully continuous, I can plot this function instead. And that's what we would do. Oops, wrong screen. There we go. That's what we would do. If I just plot x plus 1, it gives me the exact same function. The only difference is, at 2, we actually have a value. Okay? The original function looks the same, but at x equals 2, we have an undefined value. Because again, x can't equal 2, otherwise you get division by 0. But we can remove the discontinuity by instead using its simplified function. There we go. Right, that's a removable discontinuity. Right, on to examples now. Okay, so determine if the function is continuous at a. If not, what kind of discontinuity exists for this function? Okay. And then I forgot to mention what a is. Let's say for this function, a is equal to 3. Alright, well, if I put a equals 3 in there, I'm going to get a division by 0. So obviously I can't do that. But let's see what we can do with this function. I think I can factor some things out. So let's factor this. Factor an x out from the top. So we get x squared plus 2x minus 15. On the bottom, this is a difference of squares, so I can factor as x minus 3, x plus 3. Okay, numerator, I can still factor that. So I can factor that as x plus 5, x minus 3. Okay, because we can look for two numbers, multiply negative 15, add to plus 2. Alright, so it looks like we can cancel out the x minus 3's. So it looks like we can remove the discontinuity by instead using this function. There's still going to be a point of discontinuity on this function though. But at a equals 3, we can remove that discontinuity by using this function instead. Okay, so at a equals 3, this is a removable discontinuity. Removable discontinuity. Okay. Right. And let's plot it just to be certain that it is a removable discontinuity. So my function was x cubed, x cubed plus x up to x squared minus 15x divided by x squared minus 9. There we go. Alright, so at x equals 3, x equals 3, there's my function. It's undefined. Okay, but let's plot the simplified function we just calculated, which was x plus 5 divided by x plus 3. There you go. So it looks very similar. They look very similar to each other. But at x equals 3, it is now defined. So we've removed the discontinuity by plotting a slightly different function, which is somewhat related to the original function. Alright, next example. So here, x squared minus 2x minus 8. Let's say we plot a equals 4. Right, can we remove this discontinuity? Let's find out. Alright, so this function would be, I can simplify the top, or at least factor the top to x minus 4, x plus 2. This will be x minus 4. Looks like my x minus 4's cancel. So I've left with this function. Yep, did I remove the discontinuous point at a equals 4? I did. So this is another example of a removable discontinuity. And let's take a look at the graph to see if we are correct. So x squared minus 2x plus minus 8. All divided by x minus 4. There we go. Looking at x equals 4, we have an undefined point. So we plot the slightly different version, x plus 2. They are identical, but this time at x equals 4, we now have an actual value. So this is another removable discontinuity. Alright, let's move on to the next example. Alright, to prove that f of x is continuous on the interval that is given. Alright, here's a function. X times square root of 16 minus x squared on the interval of negative 4 to 4. Okay, so prove that it is continuous on this particular interval. So remember, to prove something is continuous, the following must be true. The limit as x goes to a of f of x must equal f of a. So basically this is saying, will f of a exist for all values of a? Okay, and let's take a look. So I'm going to calculate the function at negative 4. I'm going to calculate the function at 4. Because this is the upper and lower limits of my interval. So at negative 4, it's going to be negative 4 times 16 minus negative 4 squared. This is going to be this is 16 minus negative 4 squared is going to be 0. Square root of 0 is 0. Negative 4 times 0 is 0. Okay, so that's great. It exists. At x equals 4, we get effectively the same situation. There we go. So this is still going to be 0. Okay, so this is great. So at the upper and lower limits, my function does exist. So that's good. So we now know that the limit exists as x goes to negative 4. The limit exists as x goes to 4. Proving every single number between negative 4 and 4 makes the function exist is actually not that difficult. Let's consider. Okay, if f is less than 4, so for example, if f was, I don't know, 3.9, then we would get 3.9 times the square root of 16 minus 3.9 squared. Will this number exist? Yes, this number exists. The actual number doesn't matter, I just need to know if it exists. How do I know it exists? Well, 3.9 squared is going to be less than 16. I can say the same thing, 3.8 squared, 3.7 squared. Basically, any number less than 4 is going to be less than 16. So this square root will always exist. Okay? Same thing can be said of negative 4. Any number greater than negative 4, like negative 3.99, negative 3.98, they will always be smaller than 16 when I square it. So this one will always exist. So we can safely say, based on just a little bit of thought, that because I guess I'll write it down here, because the square root of 16 minus a squared exists for a, let's erase that. Okay, so this square root exists as long as a sits in this interval, then the function is continuous. Function is continuous. There we go. That's how we can prove it. Okay? But we do have to check the upper and lower limits, and then think about all the numbers in between. Okay? So this function is continuous on all those intervals. Okay, we won't go through that example. Alright, so let's see. Here's another example. Which of the following has a removable discontinuity? I think there's two examples here. So we're going to look for, can I cancel out that x minus 1, or x plus 1, sorry. The top here, I can factor as follows. X squared minus 1, x squared plus 1, all over x plus 1. We have another difference of squares. This is another difference of squares here. This can factor into x, whoops, not x squared. Just erase that. This can factor into, there we go, x plus 1, x minus 1, and we have our x squared plus 1, all over x plus 1. X plus 1 cancels, so this has a removable discontinuity. The next one here. Can I get rid of my x plus 5? Let's take a look. Let's see, this will factor, the top will factor into x plus 2, x minus 5. No, this one does not have a removable discontinuity. The x plus 5 in the denominator is still there, so it has a discontinuity at, x equals negative 5. Okay? And it's not removable. So it'll probably be an infinite or a jump discontinuity, but given it's a rational function, it's most likely an infinite discontinuity. Alright, so that kind of covers our talk about discontinuous functions. Here's the assignment. Good luck with it, and if you have any questions, come see me in class.